Time for a walkthrough of the code that steps through QRFactorization, and then it iterates the iterating QRFactorization method to find the top level eigenvalues. So let me go ahead and clear my screen and show you that I have a sample matrix A plugged in. This is actually the matrix directly from, I believe, let me check. Yes, second row is the same, third row, same. Yes, it's the exact matrix done in example 5.4. So if we use MATLAB's built-in function for eigenvalues of A, you get negative 70, 56, 114.95. So hopefully we get the same eigenvalues in our numeric methods. Now, while we're on the subject, it's important to know that you can actually get both eigenvectors and eigenvalues out from MATLAB. So it's going to produce enough information that if you give it two output matrices, you can receive all the corresponding eigenvectors. So each column vector will be the eigenvector corresponding to its respective eigenvalue down below. In this E matrix, you have negative 70, 56, and 114.95. Those are the eigenvalues that were fed out previously. Split down the diagonal because that's just a pretty typical form. So that's what we're targeting. If you know eigenvalues, it's pretty easy to calculate eigenvectors if you need them. I, in practice, usually stop at eigenvalues. Eigenvectors can have some mathematical significance. They can give you some direction, but for practical engineering problems with boundary value conditions, yeah, eigenvalues are where the ticket's at. All right, so I'm going to, we'll probably just revisit that later, but those are the numbers that we are seeking. So QRFactorization, you see the function down below. Let's just run it once to show you what's going on, if I can spell. Not of R, but of A. So we feed it a matrix A. It calculates some bumble of coefficients. But as is tradition, I've forgotten to add in two possible outputs. We're factoring it into two different matrices. So Dr. Hayes, you should probably put two different outputs available for it. So now we have Q and R matrices coming out. Now it said R was going to be upper triangular. At first this looks like we have numbers everywhere. It's fully populated, but look at the exponents here on those two elements. E to the negative 15th, E to the negative 16th. It's an iterative method. It's not going to immediately skip to being completely finished. So well, we should say finished, but that's also so numerically small, it's practically zero. So this, in numeric terms, is zero. If we change our presentation mode to perhaps something like, well, it is short g. How interesting. Okay, I guess MATLAB just wanted to really make sure we knew there was a 34733 out there, 14 decimal places to the right. That is QRFactorization's output. Let's look at how it's actually calculating this. Again, if you want to, I would encourage you to have example 5.3 out and follow along here because the process follows exactly the same. It's a very process-driven operation. So in matrix is the size of your input. The input here is R. Our typical input is A, but for whatever reason, this one's different. N saves the top in matrix. Is that a function I'm not familiar with? Let's see here. What is? Nope. All right. In matrix could have multiple vectors. I don't know why they took an extra step to do this, but they're just wanting to make sure that N, when it contains the size of matrix R, they just took another line to save off the first variable. So they ate a variable that was a temporary entity to just save off the first value. Well, guess what? If you really wanted that, just do this. That will give you the size of R in the first dimension. That should be an equivalent operations. Takes one line instead of two. So I was not misinformed. There was some mysterious in-matrix function in MATLAB I'd never heard of. It's just that the code written by the textbook was using an extra line to maybe do something they didn't have to. Whatever. Not a problem. It still works. Just an opportunity for a tiny, minuscule, insignificant amount of efficiency. I is the definition I. Again, that's an inbuilt function for the identity matrix of size n. Q equals I. That's an initialization step. You notice for believe, halfway through the first iteration, left-hand page, page 180 in your textbook, that for the first step, Q equals just H. What's really happening that they didn't show there is that the initial guess for Q is the identity matrix, which is why H comes out as the exact equivalent of Q. Well, that's the initialization. That lets us be nice and just use the same exact code for every iteration, not have to write a special case loop for the first step. So now you're going to go from j equals 1 to n minus 1. Now that is following the number of operations required as defined in step 1 of the algorithm for finding the eigenvalues with QRFactorization and iteration method on page 182. So they tell us very specifically it will take n minus 1 steps. So if you have a 10 by 10 matrix, that's 9, 5 by 5, it's 4, 3 by 3, it's 2. If you have a 2 by 2 matrix, you're only going to take one step to achieve full QR factorization. Thankfully, it's an operation that has a defined maximum. Okay, so J is our iteration step. You go through and first define the column vector C. So that is R, your input, all rows, column J. So for the first step, first column, second step, second column, etc., etc., etc. C, first row of, oh, interesting enough, it's an array. Okay, so this is where you blank out zeros going down from the top. So C from the first element, I shouldn't say first row because now C is a vector, not a matrix, as defined in line 14. So the first element of C to J minus 1. So if it's a first operation, it's from 1 to 0, so it doesn't really do anything. Second operation, so it'd be 1 to 1, so it only blanks out the first element. Third operation, it'd be from 1 to 2, so it blanks out 2 elements. So you can see each time it's the operation cycle, J, minus 1 element gets it blanked out to 0 in the matrix C. You can see this again in the example 5.3. In the first C matrix, it's fully populated. It's a three element vector because it's a 3 by 3 source matrix. The second version of C has a 0 in the top, and then the third version of C, if it were necessary, which it's not, would only have 1. E. Okay. It started by doing rows from 1 to n, so it's of size equivalent. Notice there's no previous initialization of E. This is where it's created and set. From 1 to n, it's a vector. 1 column equals 0. They could have used the zeros matrix and put the size there, but whatever. This is another way to do it. So 1 to n rows equivalent to the number of rows in the input matrix R, as defined previously up here in step 10. And they're all zeros to begin with. So now they go through the if statement where they figure out if a particular location should be 1 or negative 1. So if you look at C of J, now notice this is just one location. For the first step, C of J is 1. Second step, C of J is 2. So it's basically the top element of C that is left living. Everything else got blanked out. So if the topmost element, or the leftmost, depending on how you want to think about this, I guess they're doing it by rows. C is from 1 to J minus 1. Yeah. Okay. They are taking that topmost element, and if the coefficient of, if the sign of C is greater than 0, meaning if it's a positive number, then you put a 1 in that location of the E matrix, which is otherwise 0 everywhere. If the sign of that C coefficient is negative, then you put a negative 1 in that E location, which is otherwise the E vector is 0 everywhere. So this is just strategic placement of a inverting or non-inverting 1. So lastly, this is a nice step. This is actually the short way of calculating the Euclidean norm of C. If you think about it, C prime times C, that's actually just a horizontal vector times a vertical vector, which has the outcome of multiplying every individual component of that by each other, by itself, basically squaring each element and adding them all together. So square root of the sum of the squares, that's Euclidean norm, that's length. V, definition. This is definition equation number. Let me flip around and find it in the text. That is equation 539, very explicitly. That is your householder matrix. By definition, Q equals Q times H. Now, remember, this is why it was important on the very first step that we established Q equal to I. Otherwise, it wouldn't know. It wouldn't have a definition for Q initially, and that would crash. But so the first step, it's I times H. Every subsequent step, you're updating Q. And if you know what Q is, you can take the next step. Do R is H times Q. So H, again, householder matrix times the existing value for R, which initially was your input. So it's initially your coefficient matrix, but every time you go through this for loop, you're updating it. The householder matrix multiplied by R eventually moves this into upper triangular form. So after n-1 iterations, you've achieved full upper triangular, and you are set to go. So that is a walkthrough of QR factorization. We have achieved everything necessary to do that in matrix not found. Oh, help in matrix, yeah. So again, as an example, if we just run QR factorization of our A input matrix, we do achieve upper triangular form. If you see something alarming like that, ignore it because it's e to the negative 15th, e to the negative 16th.